Hello students, welcome back to yet another session in a final unit where we are going to see calculation of summer and winter air conditioning load. So this is a very simple topic we will discuss in today's session, and then we have a few more topics left out in this unit. So these are all the topics we have seen, and today we are seeing the calculation of summer and winter conditioning load, and then classifications and layouts of plants, then air distribution system and filters, and air conditioning system with controls, temperature, pressure, humidity, sensors and actuators, uh, and safety controls. So these are the topics left out in this unit. We will be discussing in further sessions, and we will be completing in another three more sessions. So calculation of summer and winter air conditioning load. The term air conditioning load refers to the total amount of heat energy that must be either removed from in summer or added to in case of winter a space to maintain the desired indoor conditions. Already we have seen human comfort in earlier session, and whereas either heat to be added to the room or heat to be removed from the room, so that depends on the weather conditions, either summer or winter. The indoor design conditions are defined by dry bulb temperature. Already we have seen all this. Relative humidity, air motion and cleanliness. The load calculation is critical for sizing the air conditioning equipment. Sizing the air conditioning equipment, and the size of air conditioning equipment is very important. So that can be determined using the indoor conditions. So designing ductwork and estimating energy consumption. So these are the three factors. The load calculation is critical for these three factors. So classification of loads, summer air conditioning load. In summer, the system removes heat from the space, includes both sensible heat, temperature rise, and latent heat, moisture content. So both sensible heat and latent heat are very important here to consider. Types of summer loads. These loads are like this. External loads, the solar heat gain through walls, windows and roof. So this is what we have discussed in our earlier session. And heat gain due to outdoor air infiltration and ventilation. So internal loads may be occupants, so metabolic heat. So occupants also exhibit heat. And lighting and electrical equipment, appliances and process heat. So moisture generation and human activity. So human activity is also one of the load here. So he may be sleeping, or he may be walking, or he may be doing some other work inside this space. So whenever he is doing the treadmill exercise or similar to that, there the human body exhibits more heat. So classification of loads again. Winter air conditioning load is heat. The in winter the system adds heat to compensate for heat losses from the conditioned space. So from the conditioned space, heat to be added here, and only sensible heating is considered under most winter conditions except in dry climates. So only sensible heat is to be estimated here. And types of winter loads are the heat loss through enclosure, and transmission loss through walls, windows, floors, roof, infiltration and cold outdoor air, ventilation requirements. Outside air brought in must be heated to indoor temperature. Desired humidification if the relative humidity is low. So components of summer air conditioning load, the heat gain from solar radiation. So we have seen about solar radiation in this unit, beginning of the unit, and how it impacts the air conditioning load. Also we have discussed there, and we are recollecting that. So heat gain from solar radiation through transparent surfaces like windows, So Q equal to A into SHGF into SC into CLF. So here the SHGF is nothing but solar heat gain factor, and SE is shading coefficient, and CLF is cooling load temperature difference factor. So cooling load temperature difference factor, and conduction through building envelope is through walls, the roof and glass. The Q is the heat transfer, so that is equal to U into A into T naught minus Ti. So U is overall heat transfer coefficient, A is area of the surface, and T naught and Ti are outside and inside temperatures. Infiltration load using air change method or crack method. So estimated as Q equal to 1.2 into ACH into V into T naught minus Ti. So ACH is nothing but air changes per hour. V equal to volume of the room in meter cube. So components of summer air conditioning load, even people, right? Internal load is due to people. Sensible and latent heat per person based on activity level, equipment based on rated wattage and operating factor, and lighting Q equal to W into use factor into ballast factor into CLF. Ventilation load, outside air introduced must be conditioned. So Q sensible equal to 1.2 into V into T naught minus Ti. So Q latent equal to 0.68 into V into W naught minus Wi. So V dot, that is volume flow rate of air in meter cube per minute. So W equal to humidity ratio. So winter air conditioning load components. So transmission loss, the heat loss by conduction Q equal to W into A into Ti minus T naught, and the infiltration load is cold air entering must be heated. So Q equal to 1.2 into ACH into V into Ti minus T naught. So ventilation load equal to fresh air requirement needs to be heated. So Q equal to 1.2 into V dot into Ti minus T naught. Humidification load, it is optional. In cold regions, humidification is essential. So Q latent, it is related to Q latent equal to Ma into H vapor minus H liquid, and heat vapor equal to enthalpy of vaporization, Ma equal to mass of added water vapor. So design procedure and its summary. So summer load. So here define indoor and outdoor design conditions. So winter load is also same, and calculate conduction and solar gains. So here in during winter, calculate conduction losses, estimate infiltration and ventilation, and here estimate infiltration and ventilation losses, and account for internal heat sources. So in internal heat sources should be considered here. Check if internal gains reduce heating load. So calculate sensible and latent loads. Here add humidification if required. So total cooling load equal to sensible plus latent. So total heating load equal to sum of sensible losses. So these are the summary, design procedure and summary. So important considerations here. So coincidence factor. So not all internal sources are at a peak simultaneously. So diversity factor. Not all areas reach peak load at the same time. So CLTD, CLF and SCL method. So this is nothing but cooling load temperature difference, cooling load factor, solar cooling load. So that is ASHRAE method used for accurate dynamic load estimation, and software tools can be HAP, Trace and Energy Plus used for precise load calculations. So we have dedicated softwares available. They are nothing but a HAP, Trace and Energy Plus, and also we have few more softwares, and these are popularly used software tools for calculating the precise air conditioning load. And accurate estimation of summer and winter air conditioning load is critical for designing energy efficient HVAC systems. So here, while summer load considers both sensible and latent heat Winter load primarily involves sensible heating and humidification. So here a clear understanding of heat transfer, psychrometry and human comfort is essential to predict the load calculations. So one example we'll see. So first example is summer air conditioning load calculation, and the next example winter load calculation. And problem statement: a room has the following specifications. Dimensions are 6 by 5 by 3 in terms of length, width and height, and the number of occupants are 5, so considered to be light work. So lighting load is 100 watt, equipment load is 1500 watt, glass window size is 2 meter square on west wall, and W U wall. So wall U value is 2.0 watt per meter square Kelvin, and glass SHGF equal to 500 watts per meter square. Outdoor conditions are 35 degree Celsius, that is dBT, and 60 percentage, that is RH. Indoor conditions, indoors design conditions equal to 25 degrees Celsius dBT and 50 percentage RH. So air infiltration is 1 ACH, and ventilation requirement that is 0.2 meter cube per minute per person. So room volume V equal to 6 into 5 by 3, so that is 90 meter cube. So transmission load through walls, so assume external wall area is 20 meter square. So we are making the 20 meter square simple assumption here. So q wall equal to u into a into t naught minus ti, so that is becoming 400 watts. So solar heat gain, so solar heat gain through glass, so that is Q glass equal to A into SHGF, so that is equal to 2 into 500, so that is 1000 watts. So then step 4 is internal load. Occupants are also present. So it is light activity. Sensible heat per person equal to 75 watt. Latent heat per person, so that is equal to 55 watt. Q people sensible equal to 5 into 75 equal to 375 watts. So Q people latent equal to 5 into 55, 275 watt. So lighting is Q lighting equal to 1000 watts, and equipment equal to Q equipment equal to 1500 watts. So infiltration load, that is sensible only. So Q infiltration equal to 1.2 into ACH into V into T naught minus Ti equal to 1.2 into 1 into 90 into 35 minus 25. So it is coming as 1080 watt. So that is the sensible heat only, and sensible load only. So that is infiltration load. So let's next step is ventilation load calculation. Volume flow rate equal to 5 into zero point 0.2, so that is equal to 1 meter cube per minute. So that is equal to 1 into 60 equal to 60 meter cube per hour. So sensible load Q sensible comma ventilation, that becomes 120 watt. So latent load, assume W naught minus Wi equal to 0.005 kg. So moisture, that is kg, moisture per kg of dry air, and Q latent equal to 0.68 into 1 into 60 divided by 60 into 0.005 into 1000, so that is equal to 3.4 watt. So typically this value is larger. It is simplified for demonstration purpose. So the summary here, the load component sensible, so wall conduction, glass, solar gain, occupants, lighting, equipment, infiltration, ventilation. So the total, sensible heat gain here is 5475 watts, whereas in terms of latent it is 278.4 watts. So now whatever we have calculated, and that should be tabulated and should be calculated. Total should be calculated, and then grand total cooling load is equal to 5475 plus 278.4, so that is equal to 5.75 kilowatts. And then winter load, winter air conditioning load calculations. So a classroom 8 meter by 6 meter by 3 meter needs heating in winter. So indoor design 22 degrees Celsius, outdoor design 5 degrees Celsius, wall area 60 meter square. So U is given here 1.5 watt per meter square Kelvin, degree Kelvin, and window area is 10 meter square. So U equal to 3 watt per meter square Kelvin, and ACH is zero point 0.5. Ventilation requirement is 0.15 meter cube per minute per person for 20 students. So 20 students are present inside the room, and the volume of room should be calculated. V equal to 8 into 6 into 3, so 144 meter cube. And the transmission losses walls, so q wall equal to 1.5 into 60 into 22 minus 5, so 1.5 into 60 into 17 equal to 1530 watts. And the windows, q windows equal to 3 into 10 into 17, so that is 510 watts. So infiltration load equal to 1.2 into zero point 0.5 into 144. So that is becoming 1468.8 watt. So total flow 0.15 into 20. So that is 3 meter cube per minute. So that is 180 meter cube per hour. So Q ventilation is equal to 61.2 watt. And the total heating load, now we have to calculate all this heating load, and this is coming as 3570 watts, so 3.57 kilowatt. So we can convert into kilowatt. So that is all about the winter and summer air conditioning load calculations, and you can refer the books. So these are the books. You can refer Kurmi book. It is not much given in Kurmi, but we can refer that book. And also for additional information, you can refer this e-content, e-resources also. So there ends this topic. We will see next topic in next session. We stop here, students. Thank you. We will meet again in next session. Thank you, students.